So, hi everyone. The title of my presentation is on the security of millimeter wave vehicular communication systems using random antenna subsets. So, to start the motivation of this work, like conventional, like any communication system, vehicular communication systems are subject to attacks which could jeopardize the efficiency of transportation systems and also may cause physical harm to drivers. And some of the attacks include eavesdropping, message replay attacks, and message falsification. So in eavesdropping, an eavesdropper could simply, with a sensitive receiver, could simply sit and monitor and store all the information of the drivers, and this poses a privacy violation. In message replay attacks, an eavesdropper could simply store a message and then replay the same legitimate message after some time, and with the intent to distort or disrupt the system. In message falsification attacks, an eavesdropper could receive the message, modify its content, and then broadcast it to all the vehicles with the objective of causing harm. So all of these threats or concerns motivate secure algorithms to secure the communication links. So there have been some encryption techniques for lower frequency systems. However, these techniques are not suitable for millimeter wave systems. And the reason for this is that they require exchange of keys, which is a resource intensive, this exchange. They require the broadcast of public keys, which is not possible in millimeter wave due to the high path loss. Also, these encryption techniques, they require a key distribution and management, which becomes challenging as the network scales. And at the end, these techniques fail if the keys are compromised. So these challenges motivate physical layer encryption. So in physical layer, a transmitter with a large number of antennas uses part of its antennas for communication, and the remaining antennas to jam eavesdroppers or possible eavesdroppers. And these antennas, the remaining antennas, are used to cause a jamming signal, or what is commonly known as artificial noise, in the null space of the channel of the main receiver. While these physical layer techniques were effective for lower frequency systems, most of them are not suitable for millimeter wave systems. And the reason for this is because of the hardware constraints the millimeter wave systems. While some, of course, this is with the exception of one technique, which is known as the switch array technique. And this is suitable for, it has been shown to be suitable for millimeter wave systems. So what happens in this switch array technique, which is this second technique here, is that a base station with multiple antennas uses only a few antennas for coherent transmission, and also at the same time causes some sort of jamming to possible eavesdroppers. While it's shown to be effective, this technique actually has two drawbacks. One of the drawbacks is that this technique only uses a subset of antennas, and the remaining antennas are idle. That means the technique is not fully exploiting the array gain. The second limitation of this technique, which is the switch array technique, is that it requires antenna switches, and this, of course, adds to the complexity of the array. And to add to that, also, it has been recently shown that this technique can be breached. So the approach that we take in this our proposed work is to design a beamforming technique that uses, first of all, it uses all of the antennas to beamform to a target receiver. It uses all of its antennas to beamform and at the same time randomize the side lobe. And by randomizing the side lobes, we are distorting the transmission to eavesdroppers. So the idea is as follows. So here we have the main beam. You see, it's mainly constant. But as you see here, the eavesdroppers, because of this randomization of the side lobes that we are doing, receives a jamming signal. Doesn't know actually, receives a distorted signal. So doesn't know actually what we are receiving. And as I said, the proposed approach is based on analog precoder design. It exploits all the transmit antennas. And as a result, analog design respects millimeter wave hardware constraints. Side lobe distortion randomizes the symbol at the target eavesdropper. And since all antennas are used, we do not need antenna switches in this design. So to start with the system model, this is the system model. So we assume a transmitter and a receiver, and there is a line of sight between them. So this is, and we also adopt the two-ray model, which is widely adopted in the literature to model the channel. As you have seen here, this is our channel H. We have G is our gain due to the reflected path, and this is our channel. The transmitter structure is shown on the right, which consists of simply phase shifters and a single RF chain. So it's an analog architecture. To show the received symbol or signal at the receiver, this is our received signal, and you see we have here K and theta. So theta is the angle of departure, and K is the symbol index. So that means our received symbol at the receiver is a function of the symbol index. And then here we have the transmit power, we have the path loss, we have the NR is the receive antenna gain, and then we have the transmit receive channel, which is this H of theta, and we have our transmit precoder, the symbol plus noise. So the objective in this work is to design this F using analog, just based on analog beamforming, using simply just phase shifters and a single RF chain, to design this F so that we could distort the symbol at eavesdroppers, but at the same time maintain a constant beam at the target receiver. And these are the assumptions that we laid down based on our for our model. So we have a two-ray, we assume a two-ray line of sight narrowband channel with perfect synchronization between the transmitter and receiver. Transmitter is assumed to be equipped only with the receiver's angle of departure. That means the transmitter is unaware of any potential eavesdroppers. And all receivers, the target receiver, or if it's an eavesdropper, are assumed to have perfect channel knowledge. So here I'm going to explain how the proposed technique works. So if this is your antenna, your antenna array, the idea is to choose M antennas and co-phase them so that they coherently combine at the target receiver. And the remaining antennas are selected so that they destructively combine at the target receiver. And with every symbol transmission, these red antennas, or these N, if you have a total of N antennas, these N minus M antennas are randomized. So these are random antennas, and they're selected after every symbol transmission. So for example, if you select these blue ones here to transmit symbol 1, to form a beam that coherently combines, you are selecting these red ones, right, to destructively combine at the target receiver. But at symbol 2, the locations of these antennas are changed. So for example, instead of selecting antenna 2, so this antenna 2 might become a blue, right? But then this antenna might become a red. So we randomize all these red antennas after every symbol transmission. And just to give you an idea what this will do, I have plotted the beam pattern. So you see this is the normalized beam pattern and at a receiver at an angle of departure of 90 degrees. So first of all, look at this red pattern. This red pattern is for an antenna which we're using all antennas, and we're not doing any sort of randomization. There's nothing. So this is the ideal case actually, where we're not doing any sort of switching or pattern randomization. So you see this is constant. We're sending with every symbol, this remains totally constant. But these here, you see these here, symbol 1, symbol 2, symbol 3, which is the blue, the green, and the purple here. You see that with every symbol, what happens? The main loop is constant, but every time we're getting what? We're getting a random beam pattern. And this distorted beam pattern is useful. Why is it useful? Because an eavesdropper is likely to occur to be where? In one of these locations. So that means an eavesdropper is going to get a randomized pattern or a totally random symbol. However, your main target receiver is receiving a constant symbol, or you can see the gain is really constant. And how could you vary, if we want to vary the distortion power? All we need to do is just vary the number of antennas M that are used. So if you select lower number of antennas M, that means you're selecting higher number of antennas to cause this randomization, right? And what happens is that the amplitude of these beams here will increase. And this is just a function of the number of antennas you use for destructive combining. So therefore, destructive combining at the transmitter distorts side lobes and also jams possible eavesdroppers. To go into the precoder design, the analog precoder design, you see that the analog precoder design is a function of the symbol index. So with every symbol, we are using a different, we are using a new precoder. We are using a different beam. And this is just a normalization, and since it's only analog beamforming, we're only changing the phase here. And the phase is what? This is the phase, where this is your theta R. So, and this n belongs to one of these antennas. So you see this n here are random variables. And this n here belongs to this set, or this set, or this set. And all of these sets are chosen at random, and they vary with every symbol, with every transmitted symbol. If we look at the received signal based on this design precoder F, we see that at the target receiver, at theta equals theta R, we're going to receive, so NR is my array gain at the receiver. You simply have your channel multiplied by the precoder, multiplied by S plus additive noise. You're going to get here at the end what? Your information symbol, your effective channel gain, and a constant array gain. The array gain is constant here because we said that we are designing all of these antennas to do constructively, so these M antennas are constructively combining, and then you're using another M antennas to destructively. So the interference actually, since it destructively combines, it doesn't affect much of your array gain, just maybe with a small array gain loss. But if you look at the signal received at a potential eavesdropper at theta does not equal to theta R. That means it's somewhere not within the target direction of your receiver. What the eavesdropper is going to get an information symbol, effective channel gain, where GE is the channel gain of the eavesdropper, and this is NE is the array gain at the eavesdropper multiplied by beta and additive noise. So beta here is what? Beta here is a random variable. And this random variable actually is a function of K, is a function of this transmitted symbol. So we see here, while the array gain is totally constant at your target receiver, the array gain is a random variable at your eavesdropper. And since this is a random variable, this whole expression here, what the receiver is going to get, a random variable. And the characteristics of this received signal, as we have shown in the paper, this beta here, it turns out to be an as if Gaussian white noise. And so therefore, we term this, we call this term artificial noise in this paper. And as we have shown that this beta actually depends, is a function of the number of antennas M. And as we will show in the simulation, the more antennas that you use, the less the variance of this beta becomes. So therefore, the number of antennas should be selected carefully. So to show some simulation results, what we are doing here, the setup that we're using, we're assuming a 60 gigahertz system with a bandwidth of 50 megahertz, transmission power of 37 dBm. Standard two-ray channel model is assumed. Transmitter is equipped with 32 antennas and a single RF chain. Receiver and eavesdropper are equipped with 16 and 32 antennas. The subset size that's used is 75%. So the number of antennas that are used are for coherent beamforming are 75% of the total number of antennas, while the remaining 25% in this figure here were used to randomize the side lobes. Match filter received beamforming is assumed. Distance from the receiver is 30 meters and eavesdropper is 10 meters. And the receiver is located along an angle of departure of 100 degrees. As a performance measure, we adopt the secrecy throughput, which is actually the rate at your target receiver minus the rate at a possible eavesdropper. So this is the secrecy throughput, which is bits per channel use. And what is required is that you should always have high secrecy rate at non-receiver direction and zero secrecy rate at your receiver direction. This is what's required. This is what is required, ideally. So if we look at the simulation here, we have for NT equals to 32 and NT is equal to 16 antennas. We see that our technique, this is our technique, and we also compare with the switched array technique that I have described previously. We see that both of these techniques, they achieve high secrecy rate at possible eavesdropper direction, except at our target direction, they receive zero secrecy rate, which is what is desired. Here with the black plot, what we have conventional antenna arrays. That means we're using all of the antennas without any side lobe randomization. And we can see that the secrecy rate is lower and not as high as what is achieved by these techniques in both plots. And the reason for this is that since the side lobe is constant, an eavesdropper, all it needs to do is have an antenna with a sensitive antenna. So if it increases its array gain, it can eavesdrop and obtain that information and use it for malicious activities. But our technique actually maintains a higher secrecy rate. That means it's able to add some immunity and enhance the secrecy of the communication link. In this figure here, what we are doing, we are actually varying the subset size. Our number of antennas is 32. And also we're comparing with the switch array technique. So we see that the proposed technique, as the subset size, which is the number of antennas actually used for coherent beamforming to the receiver, increases, our secrecy throughput increases, and this is what's expected. But after some point, it plateaus, and then it starts to decrease. And the reason for this is that as you increase M, the remaining number of antennas, which is N minus M, which are used to randomize your beam pattern, becomes small. So if you're having a smaller number of antennas to randomize your beam pattern or cause artificial noise, what you're doing actually, you're maximizing the SNR at an eavesdropper. You're actually increasing the SNR at an eavesdropper as you increase M. So therefore, there is an optimal value of M, because you have to strike a balance. You have to strike a balance between the beamforming gain and the artificial noise that you want to generate at a potential eavesdropper. So there is an optimal M that actually maximizes this secrecy throughput. We also see that our technique performs better, provides better throughput when compared to the switch array technique, using the same number of antennas. And as we indicated previously, the reason for this is that our technique uses, the proposed technique uses all antennas, and the switch array technique only uses a subset of antennas, while the remaining antennas are simply idle. So this is why we have this gap here. And also, if we see here at part B, we look at the beam pattern variance. So we're looking at the variance of this signal that's received at an eavesdropper. We see that our technique, the proposed technique here, provides a very much higher variance when compared to this technique here. And the variance, of course, reduces and becomes 0 as the number of antennas equals 32. So if the number of the subset size becomes 32, that means you're using all of your antennas for transmission, right? So that means there is no antenna, there is no remaining antennas used for beam pattern randomization. And that's why we have a 0 here. And as the number of antennas is low, that means most of your antennas are being used for, in the proposed technique, most of the antennas are being used for side lobe randomization. But when compared to the switch array technique, only 2 antennas are used. When compared to here, 30 antennas are used. That's why we have this high pattern. Therefore, the number of M, like I reiterate, this M is a design parameter that should be designed to maximize the secrecy throughput. So in conclusion, large dimensional antenna arrays can be exploited to jam eavesdroppers. The proposed technique is keyless and transparent to existing receivers. And also, the proposed technique can be used to augment higher layer security techniques. Thank you.